Hello and welcome back. Let's talk about line integrals. Here I have my 3D representation of my line integrals, which if you have been watching my videos in the past, you would have seen me bring out a few times. And I think this is a really great representation of what a line integral truly is, because let's be honest, it's hard to draw in 3D, or at least I definitely have a hard time. If you've watched my videos, you would know that. But what a line integral is it's some integral. It vaguely represents a normal integral that we would evaluate, except this time we have a line that we want to integrate about. We call this the curve C. The curve C is right here. This is called a line integral. And so we're evaluating, like I said, over our function of x, y, because it's a function in 3D space, and we're integrating with respect to arc length. And the reason we're integrating with respect to arc length is, well, because we have a curve and not just a straight line along the y or x axis. So if you've watched my videos in the past, my videos on arc length, we know that ds actually equals dx dt squared plus dy dt squared dt. And this is really just derived using the Pythagorean theorem. And you can go back and watch my video on how it's derived. We derive it in the arc length video. Specifically arc length of parametric equations in that case. But as we can see here, we have a new variable t, and this is why we need to know our parametrization of curves in 2D space, because we're just in the 2D space when we're talking about the curve. So this doesn't really look like it simplifies the integral, but it does. It really does. What we can say now is we can integrate from t naught to t1, or t initial to t final, basically what t runs from. And we can now represent our function of xy as our function of the parametrization t times our new ds term, dx dy squared plus dy, this is dt, dy dt squared dt. And now everything is in terms of t. So I suppose we should look at an example. Let's integrate over the, or I'll leave this blank. Let's integrate over the function xy with respect to s, where your curve C is a line segment from, we'll say 0, 0 to 2, 2. This is a very simple one, but of course we could integrate over any curve we wanted. We could integrate over a circle if we wanted, or a line segment of x squared, or anything. We remember from our parametrization video that we can represent anything in a parametrization. So this parametrization will be very simple. Our r of t is just going to equal, well, how much does x change? 2. Our x naught is 0, so this is 2t, and y is also 2t. Now, our dx dt is just 2, our dy dt is just 2, 2 squared plus 2 squared is 4 plus 4 is 8. So this actually simplifies to ds equals root 8 dt. And this is why I chose something this simple. And we know that t runs from 0 to 1 in the case of a line. So let's rewrite our integral. We have the integral from 0 to 1, x, y, represented in our terms of r of t, is 2t times 2t, that's 4t squared. Let's take our root 8 outside, and let's put our dt. So this actually becomes very simple. Let's take our 4 out, 4 root 8, integral from 0 to 1 of t squared dt. And this equals 4 root 8 times 1 over 3 t cubed, evaluated from 0 to 1. This is just 4 over 3 root 8. Very, very simple. So that's really all I have for you in terms of line integrals. Of course, if you guys would like for me to go over a more complicated example, I sure could. I sure could make another example on this in another video. But for now, we know our basics. And in the next video, we will talk about line integrals over vector fields. Something much more fun with much more applications in the real world. Thanks for watching.